Hello friends, today I am going to present my recent research work on analysis of nonlinear characteristic of graphene based 4-terminal ballistic rectifier using drift diffusion model. The citation information of the given paper is mentioned in the given slide. So first of all, I'm going to start with the motivation. So the scaling of the semiconductor technology enables the fabrication of electronic devices having smaller size and better performance. So when we are going to decrease the size of the device, the performance of the device is going to be better and better in terms of the speed, in terms of the power consumption, and the scaling not only improve the device speed but also generate the undesired phenomena like short channel effects. If we are going to consider the example of the MOSFET, so when we are going to decrease the length of the channel after a limit, a point is reached where the depletion region of both source and drain will touch each other, and that is called the short channel effect. So this is the undesired phenomena which will happen with the MOSFET. So researchers are proposed the various devices like cell switching diodes, 3-terminal ballistic junction, 4-terminal ballistic rectifier, and ballistic deflection transistor. So these all are the novel devices having the capability to operate up to very high terahertz frequencies, and their working principle is novel. So cell switching diode is a 2-terminal device. When you are going to apply the potential between the terminals, you will get the characteristic like a diode. The cell switching diode is planar in nature. It is having the capability to work up to the very high terahertz frequency. Recently, 1.5 terahertz response of the SSD has also been proposed in the literature. And 3-terminal ballistic junction is a 3-terminal device. When you are going to apply the potential between the two terminal, you will get the output at the third terminal, and the output resembles the same operation as that of the bridge rectifier. It's also a planar device. And third one is the 4-terminal ballistic rectifier. It's a 4-terminal device having a special type of geometry. A triangular antidote is present in the center, which will deflect the transistor charge carrier in a particular direction that will generate the bridge rectifier type of response. And finally, we are having the last one, that is ballistic deflection transistor. This particular device is the modification of the 4-terminal ballistic rectifier. The BDT is having the 6-terminal as compared to the 4-terminal in the case of ballistic rectifier, and the BDT could be used to deflect the charge carrier in a particular direction to create the different digital application like different gates, the combinational circuits, and the sequential circuit. So in this work, I'm going to present the 4-terminal ballistic rectifier with the use of the graphene. So 4-terminal ballistic rectifier. 4-terminal ballistic rectifier is a device having 4-terminal source, drain, lower terminal, and upper terminal. So it's a planar nanoelectronic device. It could be fabricated with the help of 2-dimensional electron gas heterostructure or the novel materials like graphene. It could be fabricated using e-beam lithography and wet and dry etching process. The single device resembles the same operation as that of the bridge rectifier. So when you are going to apply the AC input between source and drain, the charge carrier are trying to cross the junction, but due to that presence of this antidote, they will the electrons or the holes will deflect in a particular direction, that is the lower side. And when you are taking the potential difference between the lower and upper terminal, you are getting the rectified type of characteristic. So the single device resembles the same operation as that of the bridge rectifier, and device is planar in nature, having very less parasitic capacitance, and it could be work up to very high terahertz frequency. So potential application of 4-terminal ballistic rectifier are like RFIDs, medical, security, imaging, and energy harvesting. So in this research work, we have simulate the device using Silvaco TCAD with the use of the graphene. So graphene is a 2D novel material having very high mobility. Uh, so the active region of the ballistic rectifier is designed using the graphene. So in this research work, we have done both type of simulation, the 3D simulation and equivalent 2D simulation, because the noise simulator is available only in 2D. So 3D structure is going to be, converted into equivalent 2D structure. So in this, the device is, designed on the silicon dioxide substrate, and here a backgate terminal is going to be connected, and on the basis of the backgate potential, if it is positive, the electron effect will be dominate, and if it is negative, the Hall effect will be dominate. So these are the source and drain terminal of the device, which will work as an input terminal, and here we are having the lower and upper terminal of the device, which will work as a output terminal. So when potential is going to be applied between the source and drain, the charge carrier are going to be cross the junction, but due to the presence of the antidote in the center, they will deflect in the lower direction, as more number of charge carrier will be deflected toward the lower terminal as compared to the upper terminal. So when the potential difference is going to be taken between the lower and upper terminal, it will generate the rectifier type of characteristic. So the transfer characteristic of the device is going to be shown over here, where the electron effect will be dominated on the right hand side as compared to the Hall effect on the left hand side. So again, continuing with the 3D simulations. So response has been plotted between the output potential difference and the gate potential. So when the gate voltage is, going to be varying between the -8 and 8 volt, we have noted the output potential between the lower and upper terminal. So both potential are mirror image of the each other. So here response has been simulated for the uh, two things, first with the trap and another without trap at room temperature. So if we are going to plot the response between the output terminals and the input terminal, we are getting the rectifier type of characteristic. So the response has been simulated for three different temperature: 300K, 77K, and 4K. So here Vk value of Vg has been taken so that we are getting the maximum response at the output side. So if we are going to compare here, we are getting the maximum response for the holes as well as for the electron around 2.5 volt. So here for 300K, we have put it here the response for the 2.5 volt Vg. So when we are going to decrease the temperature starting from 300 to the 4K, we are getting the better response, because when we are going to decrease the temperature, the mean free path of the charge carrier is better as compared to the overall dimension of the device, so that the charge carrier will never face any kind of scattering and they will move like a bullet. So that is why the name of the device is like a ballistic rectifier. So as we are going to decrease the temperature, we are getting better and better response. So next is the response, which is going to be plotted for the push pull and push fixed response. So this one is the push fixed response. Figure number C is the push fixed response, and figure number D is the push pull response. Push fixed is something where we are going to apply the potential difference at one of the input terminal, keeping the other terminal as a ground. And push pull response is something like Vs is equal to Vd is equal to Vs is equal to minus of Vd is equal to 0.1 volt. So when you are going to apply the 1 volt at source terminal, we are going to apply the -1 volt at the drain terminal, and this is called the push-pull response. So this response has been noted for different value of Vg. So for holes and electron, we have noted or plotted the characteristic. So the holes and the electron characteristic are mirror image of each other. So when we are going to change the value of Vg, the device could be work as a NOT gate by just changing the value of Vg, both for the push-pull and the push-fix response. So next is the AC characteristic of the device. So if we are going to consider the figure number A, this is the AC response. So pull response has been applied between the Vs and Vd with the potential of 0.1 volt, and the output has been measured at between the output terminal. So this is the ballistic rectifier characteristic, which resemble the same operation as that of the bridge rectifier. So this response has been noted at 1 kilohertz frequency. So next is the responsivity characteristic of the device. So backgate voltage affect the device characteristic in a huge manner. So the responsivity and the noise equivalent power are the very important factor which we need to consider in the case of nano devices. So this responsivity response has been measured at room temperature. Similarly, noise equivalent power has been measured at 300 K or room temperature, both for 1 kilohertz frequency at different value of Vg. So at Vg is equal to 0, we are getting the value around 10 millivolt per milliwatt, and for the holes and for the electron side, we are getting the mirror image. So as we are going to increase the value of Vg, we are getting the different values, and the maximum value we are getting at around 2.5 for the responsivity, because the output of the given rectifier which is measured by us is giving the better response at 2.5 volt, around 2.5 volt at room temperature. Similarly, noise equivalent power is inversely proportional to the responsivity, so we are getting the minimum value at around 2.5. Similarly, the responsivity and the noise equivalent power has been measured for the different frequency in figure number D. For Vg is equal to 2.5 volt at 300 K. So the given characteristic shows that the device work well up to terahertz frequency. So next, the 2D simulation of the graphene based FTPR has been done, and 2D simulation has been done because because of the only availability of the 2D noise simulator. So equivalent device geometry has been considered both for the push pull and push fix response, and the output of both push pull and push fixed has been compared in 2D with 3D. So the response give us the better resemble with the 3D if we are going to compare here for push pull as well as for the push fixed value. So the in 2D the other layer effects is compensated with the help of the background doping. So next, the 2D characteristic or 2D device structure of the device given FTBR has been used for the noise simulation of the device. So this is the equivalent structure of the device. All the terminals has been converted into the equivalent resistor response as shown in figure A as well as in B. So in the case of nano device, the noise simulation plays a very important role, because at lower frequency the flicker noise dominate, which will meet to the thermal noise at the higher frequency. So here the frequency response of the device has been measured, where the noise spectrum of the ballistic rectifier are simulated from S terminal, that is source terminal of the device, for different value of the input voltages. So the thermal noise is generated at Vs is equal to 0 volt. For Vs is equal to 0 volt, thermal noise has been generated, and when we are going to increase the value of input voltage like 0.01 volt to 0.05 volt, we are getting the flicker noise at lower frequency as compared to the thermal noise at higher frequency. So next, the response of the device has been measured. Noise response has been measured for different value of the Hughes constant, different value of the mobility. This is the Hughes constant. This is the mobility. This is the number of charge carrier. And here we are going to change the alpha n as well as, that is Hughes constant, as well as the number of charge carrier at the same time. So when we are going to change the Hughes constant, there is a change in the flicker noise of the device, and thermal noise becomes same. And when we are going to change the mobility, the flicker noise is going to be same and thermal noise is going to be changed. Similarly, when we are going to change the n, the number of charge carrier, both the thermal noise and the flicker noise will change. And the Hughes constant and the number of charge carriers, if both affect the flicker noise at lower frequency. So when we are going to change the alpha and n in same proportion, there is negligible change in the, or no change in the flicker noise, but there is a change in the thermal noise due to the change in the number of charge carrier. So on the basis of this, we are concluded that the noise is due to the number of charge carriers, not due to the mobility. So conclusion, so graphene FTBR is simulated using the drift-diffusion model. The obtained results for the 3D and the 2D geometry are compared with each other for push fixed as well as for push pull input configuration. The device demonstrates the responsivity and noise equivalent power of 89.21 millivolt per milliwatt and 97.52 picowatt per under the root hertz. Noise characteristic of the graphene FTBR suggests that the device exhibit low frequency noise or flicker noise, and is mainly due to the number of charge carrier available in the channel and is not affected by the mobility. And graphene ballistic rectifier can be used as a room temperature detector at high microwave or terahertz frequency, producing the high rectification ratio similar to the graphene cell switching diode device for various applications including the terahertz imaging. And we will get the even better response of the device if we are going to place the graphene over the hexagonal boron nitride, because it will give the smooth surface to the graphene for getting the better and better mobility. So the front page of the paper has been shown over here, and the first page is shown over here, as well as the citation information is given here in this slide. Thank you very much.